Today we are going to be talking about Newton's third law. I'm going to do things a little bit in a different order than I explained last week because, quite frankly, I think we're going to need an extra day on this particular topic because they couldn't they couldn't steer clear of today to have a special club session. So we have only a scarce few minutes. So I want to use all of them. So we're going to talk about Newton's third law, and we're going to do a couple Newton's third law examples. But this is what the real test is about. So we will be having our test a week from today, and it's going to cover the multi-body problem. Now, you have to be accomplished at the single body problem, and as we saw from your last test, a few of you are not. You have this week to be accomplished at the single body problem because the multi-body problem requires all of the things you've already done plus a few extra little steps. And that's what we're going to specifically talk about today. It's not a huge difference, but it's enough where I need you guys to be really on your toes here. The math is going to escalate a little bit. So you need to be really, really prepared to keep track of what's happening in our discussions today. You already know what Newton's third law is. There's plenty of colloquialisms that reflect Newton's third law, and I'm sure you've heard them. But probably the most famous is that for every action, there's an equal and opposite reaction. You heard that? That is a fine way to express Newton's third law. I'm going to change it a small amount, but you should probably get that in your notes, only because that's something you already remember, and you've heard it before. That is the essence of Newton's third law. For every action, there's an equal and opposite reaction. So I would say it a little different because we're talking about Newton's laws here. Because of that, I want to be very specific about how this applies. People apply this idea broadly to the universe. It's not true. That's not always true. But this is always true, that for every force, there is an equal and opposite reactive force. Or the way I would like it said is forces come in action-reaction pairs. So every one of the forces that we've seen always has a Newton's third law force with it. What most people don't fully understand, and even after a course in physics don't usually appreciate, is that these two forces act on separate objects. The reactive force acts on a different object than the first force. To understand that, let's use one that we've been talking about. We have spent more than enough time talking about applying forces to things and asking to draw a free body diagram about the forces that are acting on something. And the first force you guys have almost always talked about, and under my direction, is that every object is experiencing weight. Well, if all forces come in action-reaction pairs, there has to be a reactive pair that the weight is acting on. And that reactive pair is the Earth. If you are experiencing the weight from the Earth, then the Earth is experiencing a reactive force from you. So the Earth pulls down on you, and you pull up on the Earth. This constitutes an action-reaction pair. Now, the thing that most students don't understand is the force of gravity on you is effective at accelerating you, but your reactive force on the Earth isn't effective at accelerating the Earth. These two forces act on separate objects. That does not explain their effectiveness. The effectiveness of a force depends on the object upon which it acts. Weight is effective at accelerating you because you're not very big. So the force of gravity on you will accelerate you downwards easily. You trip and you'll fall. But that reactive force acting on the Earth has to act on the Earth. The Earth is huge. And because the Earth is huge, that force is not effective at accelerating the Earth. So although these two forces exist, the effectiveness of a force is still dependent upon the size of the object and other forces acting on the object. These two things determine the effectiveness of a force: the size of the object and all of the other forces that act on the object. So we're going to do what I tend to call a train problem. It's not going to look like a train, no, but it's a train problem. A train problem is any problem that has a series of objects in a row. So it doesn't matter whether those objects are like a set of boxes on the floor or a set of train cars on tracks. These are all the same question. We're going to do a set of boxes on the floor. And in the case of this system, there's going to be me pushing on the boxes. So I am applying a force to the first box. And the force on the first box is going to be 45 newtons. This box is 10 kilograms. This box is 5 kilograms. Now, I'm not interested in the forces acting on me. So I'm not going to be talking about my portion of this problem. I'm just going to say that I am effective at applying this force to those boxes. In a problem like this, we are going to start every one of these problems the same way we started all the others. The difference is that there's more than one object, and it doesn't matter that there's more than one object, except that each object now gets its own free body diagram. We can only study one object at a time. That's still no different. So the multi-body problem, which this is, still has to be studied as if we're studying one object only at a time. Now, Newton's law problems still have the same restrictions. The only thing we can do is find either an acceleration of our system or an individual force, and that's still true now. We're not changing any of these sets of steps. We're not doing anything different than we've done before. We just have to keep track of both objects. However, would you agree that it's unlikely that the big box and the little box can have different accelerations? Like, it's not like the big box can pass through the little box. And it's not like if you push on this box over here, that suddenly this box moves on its own. So can we agree that both boxes have to move together? That seems pretty reasonable. I mean, it is possible you could do this, and anybody who's worked someplace pushing boxes around knows that if you don't do it right, you can crush the middle box. So anybody who's worked in a warehouse or in the stock room of someplace, that happens. So if you don't do this right, all boxes usually have a crush weight on them, the amount of weight they can take before the box collapses. So let's assume these don't do that. Now, we're going to start at the first box, just like any other problem, and start by indicating that it's experiencing weight. 100 newtons of weight, actually. All right, 10 kilogram box. It's also experiencing an upward normal force from the floor. It's experiencing my pushing force. I am pushing it to the right with 45 newtons of force. But there's another surface in contact with the box, and that's the surface between the two boxes. And the only way this surface could apply a force on the first box is for there to be a normal force this way. Right? Because the normal force has to be perpendicular to the surfaces in contact. And therefore, this box, the 5 kilogram box, has to push to the left on the 10 kilogram box because that is perpendicular to the surface in contact. we good to move on? Yep.
Does friction act on?
Let's not complicate it. We'll make it frictionless for now. Friction doesn't actually affect this problem very much in that it would just add a frictional force to each box. But I don't think we need to add more right now. I think this is okay. Now, here's where student, yes, sir.
Is the arrow for the normal force from the opposite object always going to be smaller?
I am assuming the boxes accelerate because I didn't say whether they accelerated or not. So in my head, I'm thinking that the only way they could possibly accelerate is to the right. So I drew the normal force to be less to indicate that the unbalanced force is generally to the right in this problem. Does that make sense?
Yeah.
Okay. Now we could work the problem out, and if we find out the acceleration is 0, then we know that I should have drawn that arrow to be the same size. All right. Yeah. Everybody good? All right. We're going to do the other box now. And the other box has a series of forces acting on it. There's a weight downwards, which is less, 50 newtons. There's a normal force from the floor upwards, probably also 50 newtons. Don't think the box is accelerating downwards or upwards. Now here's where students make mistakes, so I want to be kind of direct with you. There is a force to the right, and it has to be equal but opposite to the normal force acting over here to the left. Those two forces are the Newton's third law pair. Box 1 pushes on box 2, so box 2 pushes on box 1. Those constitute the third law pair. All third law forces are going to have some interface where they act, a point of contact. The only time that's not true is if we're talking about gravity. So where these two objects touch, that's where the third law force exists. Now, notice the arrows have to be equal and opposite. So they're drawn in the opposite direction. And clearly, similar size should be a goal for you. Now, we've done all the work that we can when it comes to my set of steps and identifying forces that are acting on the objects. There's no strings or ropes or anything. There are people who want to know why I didn't draw the 45 Newton force on the other box. Like, why isn't it on both? I'm not touching the other box. And therefore, I'm not applying a force to it directly. My force is being carried to the other box through the fact that they're in contact here. That's how the force I'm applying to the first box gets transferred to the second box. That's how this works. The third law is supposed to be a way for us to realize how a force gets spread out over a group of objects. That's really what it's about. Now, at this point, your job is to continue to do the same thing we've been doing. Put in a coordinate system and identify the net forces that are acting in the system and come up with a relationship that is no different now. I'm gonna put in a coordinate system. I think a reasonable coordinate system is going to be one that is lined up with the direction of motion. Like so. I hope you realize that the boxes aren't going to accelerate up or down. So I'm not really interested in looking in the X direction, but I am going to look in the, I'm not really interested in looking in the Y direction, but I do want to look in the X direction. I'm going to do what I've been doing, which is follow these directions and say that I'm going to add up all the forces that act in the X direction, set them equal to MA. So for the first box, that's 45 minus normal equals 10 times A. And for the second box, that's going to just be normal equals 5 times A. And that's it. That's all that Newton's laws can tell us. Now, this is the multi-body problem. when you're done with the multi-body problem, you're going to have expressions that are going to have shared variables. The fact that the normal force acting on both boxes is of the same size means that it's a shared variable. It means that I could use it. I can do substitution here, which I want to throw into your notes now. In a multi-body problem, you're going to be doing substitution. You are going to be combining the two relationships to figure something out about your system. Newton's laws have always been the same in that they can only tell you the acceleration of the system or a force acting on the system. So in the case of this problem, I can figure out how the boxes accelerate, and I can figure out how much force there is between the boxes. But that's all Newton's laws could ever tell us. Now, solving this one is not particularly hard. This is a pretty straightforward algebra problem, but there is something here that I want you to look at and see specifically. First, does everybody realize that we're going to do some substitution here? That I can substitute in for the normal force. And this will help me figure out what the acceleration of the system is, which is the only other variable available here. So when I substitute, I'll get 45 minus 5a. That's what I'm substituting in for normal force. Equals 10a. Now, this is something I would really like you to emphasize in your notes. This is a way to check your work. If you've done everything correct, what you're about to see should show up in every one of your problems. I'm going to add 5a to the other side. When I do, on the other side, I'm going to have the sum of the two masses. This is the mass of the system. This is the one unbalanced force. And this is the acceleration of the system. When you're done and you've got your final relationship, you should see all the masses being added up. If you've done this right, you'll see all the masses being added up. If you've done this wrong, you won't. This is how you know you've done the multi-body problem right. You'll see the sum of the masses in there. Also, let's just notice this too. This is net force equals ma for the whole system. You'll see that too at the end of one of these problems. It will form Newton's law as if it was acting on the entire system, as if the whole thing was just one box with one mass. That's what you should see at the end of one of these problems. But more importantly, you should see a moment where all of the masses in the system are being added together. Now, yes, there's an answer here. There's math you can do and find out that you get 45 divided by 15 or 3 meters per second squared. That will be the acceleration of the system. And again, this problem is not particularly interesting. I'm just showing you how you do a multi-body problem. I do think it's valuable to go back and take a look at something, but is everybody up to where I am in this problem? Everybody okay? So we know the acceleration of the system. If I look right here, that means that that normal force had to equal 5a, which is 5 times 3, or 15 newtons. Everybody see that all right? Now, 10a is 30 newtons. I'm saying this because the net force on the first box is 30 newtons, and the net force on the second box is 15 newtons. What was the total force on the system? So we started with 45 newtons of force applied to both boxes. 30 newtons of that force was used to move the one box, and 15 newtons of force was used to move the second box. The bigger box required more force, so it took more of the 45 newtons. Smaller box needs less, so it took less of the 45 newtons. So this process divides force up so that each object gets the amount of force that they need to be accelerated. Now, that is the simplest multi-body problem we can talk about. There's only two ways to go from here: more objects or more interesting arrangements, but they are all exactly like this. And there's a reason why I call this the train question. So, train question. The only difference is that I'm pulling on one of the rail cars. There are things that connect the rail cars together. So instead of normal force, you'll have tension between the boxes. It's the only difference. Is that a train car, we replace normal force with tension forces. And again, it doesn't matter how many of these there are. There could be, a whole row of them, all different masses. Of course, the problem is that you've got two different sets of Newton's third law forces here. So if I say I'm pulling this with 100 newtons of force, well, you'd have to do the same problem we talked about to figure out what's going on here. Now, there are shortcuts in these problems, but most of the time these problems are pretty straightforward. There's just not a lot to do. You just have more things to do. For this problem, we won't have time to finish it. I'm pretty sure the bell's going to get us here in about 4 minutes. But if there's no friction in the problem, I don't have to worry about the up and down forces so much. Do we need the up and down forces on the last problem? No. If there's no friction, you probably don't need those forces. But this problem, let's just stay frictionless. Consider that we've got 100 newtons this way and T1 this way. There's got to be a tension that acts backwards on the car because it's connected by some cable to the other car. I go to the middle car, T1 this way, but it's also connected by a cable to the car behind it. Again, I'm intentionally making them different sizes because I think it's supposed to be a net force to the right. And finally, now, yeah, I should draw the up and down forces, but I think at this point we're going to be able to focus on just what's happening here. Now, this problem isn't much different than what we just did. It's just got more objects. I start looking at all the things that are happening. I've got 100 minus T1 equals 5A. That force on the first car. Maybe T1 minus T2 equals 10A. T2 equals 15A. Like it or not, that's a lot of substitution, right? 3 equations and 3 unknowns. It's not fun. I'll give you a hint, though. If you want a hint on solving these, the easiest way to solve these is look for whatever's in the middle. Substitute to the middle. It'll be easiest if you do it that way. So always substitute to the middle. If you substitute to the middle, you'll get your problem right quickest. and you'll always get a single relationship that will answer your question. Our multi-body problems are never going to have very many objects in them. So substituting to the middle is the best way to go. But you still have to do all the work. So you still have to solve this for T1. It's 100 minus 5a. And then you got to substitute in to create your relationship. So I'll have 100 minus 5a for T1 minus 15a for T2 equals 10a. And then I'll move everything with a to one side. And then I'm going to notice something. That if done correctly, do you see a point where you've added up all the masses together? It happens every time. If you do it right, you'll reach a point where you add up all the masses together. That's how you know you've done it right. So I think 10/3. All right, we're out of time.